Mr. Foster will give y'all out the lab procedures and the labs that y'all are required uh, to do. Uh, and there's several labs that are homework labs. And the first actual lab that you'll be doing was he'll get you in the disconnect box up there and you'll measure the voltages in there. And then you're going to learn how to wire this transformer, like I said, which would be probably the first actually hands-on lab you'll do is actually wiring up the transformer. So we'll look at some transformer basics. Let's see. I hope this is a new computer. I hope it's got, yeah, it does. Somebody broke the tip off of this thing. I wonder, I wonder who did that. Probably me. I probably ran over it with my. Maybe y'all can hear it. This is a really good PowerPoint slide. I mean, a real good. It might not even. Questions? Pretty straightforward, right? Huh? No. What is a transformer? Oh, what happened? Yeah, this one doesn't have the screws on it. Yeah, like my other one does. So, so what's a transformer? Yeah, if you look up transformers on YouTube, that's what you'll get. So if you want to get information about transformers, you have to type in electrical transformers first. But what are electrical transformers? Well, somebody just made a big mistake and you just lost your job. They do not change power. Power in equals power out, right? You understand that? If they were 100% efficient. Most transformers are at least 95% efficient, so usually when we get to them, we assume that it's okay. Alabama Power would have to really worry about it, but we don't have to worry about it, right? You understand? So that transformer right there, we'll say that the power out equals power in. We don't create, transformers do not create work, right? You understand? All they do is transfer power. Power in equals power out. So that's a good thing where you'd lose a job if you went into somebody who really understood transformers and you said they increased power, right? You understand that? They don't change power. So when I talked about this, if you turn on a 100-watt light bulb, then the power company, if all the transformers were 100% efficient, they would give you 100 watts. Every transformer, 100 watts in, 100 watts out, 100 watts in, 100 watts out. What we change is transformers change the watt, voltage and the current. So if the voltage goes up, the current is going to go down to deliver that power. Now you said that don't make sense because in Ohm's law we learned that if voltage goes up, current goes up. We're not talking about the load, we're talking about the source, right? You understand? The source of the power. Transformers do not generate power, they transfer what? Power from one AC circuit to another using magnetic coupling. Input is AC and the output is AC. They work on the principle of electromagnetic induction, and we had a pretty good idea over here just by using that battery. What determines the amount? The strength of the magnetic field, right? The number of conductor loops, and the speed of the motion. Of course, our motion is the same, and that's why AC works, because AC automatically, the magnetic field is automatically in what? In motion, right? So we know about the core, right? You understand that? So what's the purpose of the core? What's it? The magnetic field. Everybody knows that metals concentrates magnetic fields, right? You understand that? They have a tendency to move through the metals themselves. So the purpose of the core is to get a real good magnetic coupling between this and this. There is no voltage coupling. We have there. If this side is grounded, this side don't have to be grounded. So we use transformers. We call them isolation transformers, where they'll be 1-to-1. So that means voltage in equals voltage out, but we don't bring the ground through. And that way, the problem with having things grounded is it's nice because why don't we ground all our metals? Why do we like in around electrical places? Why do we like to ground these metals? Huh?
To prevent shocking. So the voltage or the power will actually go to the actual ground wire instead of going to us.
If we have a short circuit. But that's not the main reason. The main reason is they're metal. So I have a metal. I have a change in magnetic field. that magnetic field goes through that metal, it would induce a voltage on it, and these cabinets would literally build up a voltage on them. They would have a voltage on them if we didn't do what? If we didn't connect them to ground. So one reason we ground all these metals is so they won't build up a charge, right? You understand, because they are conductors. And another reason, it gives us a path to ground instead of going through us when we have short circuits. So the function of this guy right here is we don't want it to be a conductor. We want it to be a conductor of the magnetic field. We don't want it to be a conductor. So what do they do to make it not a conductor? So what happens when I put the magnetic field in here, it induces a voltage which does a current, and this would be really, really big, and it would be a big current, and it would get hot, and the transformer would be very, very inefficient. So what we do is we break this core up into hundreds of individual little plates, and we insulate them from each other. We call those laminations. So if you ever look at an AC transformer or even an AC relay, I can actually show you a relay that uses that same feature to break up the magnetic field. Let's see if I can find it. I don't know if I've got a transformer. I have an armature for an AC motor, and you can see the laminations in this to break up the magnetic, to use to concentrate a magnetic field instead of, so here's a transformer. So when you look at the actual core, you'll see it split into hundreds of individual plates. And then what they do is they electrically isolate them. They're coated with a lacquer. And what that does is insulates them from one another. So it means the little eddy currents that's put into one will not combine with all the rest of them, right, and create basically a shorted secondary. So that's one of the things. So anything that's going to transfer a magnetic field, we're going to use laminations. So I can come up here, and this is the rotor. This is the rotor off an induction motor. When you look at the actual core here, the actual rotor, it's split up into laminations. These are the conductors that carry the magnetic field. This is to concentrate the magnetic field around those conductors, and it's what? It's laminated. And what does that do? It prevents from all those eddy currents from doing what? From combining, right? You understand, and creating a very inefficient. So we don't want it to be a conductor of electricity. We want it to be a conductor of a magnetic field. So transformers will still get warm. And in fact, really, really high wattage transformers are going to be hot. So, you know, if you get into a substation, transformers are going to probably be liquid cooled. And then they're going to circulate that liquid just like your car does, circulates that liquid through a regulator, to a radiator, right? You understand? You have fans on. So this is the symbol of a transformer. This would be single winding transformer. So we have the primary. All your primaries are going to point toward the source of the power. And then we have our secondaries. Your secondaries are always going to point toward the load. Even if you go from transformer to transformer, like in the power grid, you're going from substation, you might drop it down for safety, but then you can run into another substation and step it up and send it. This indicates iron core, and why it's drawn as a dash, because it actually indicates a laminated core. So this is a symbol for a transformer, right? Doesn't tell you if it's step up, doesn't tell you if it's step down. We know it consists of three parts. We have a primary winding, then we have a secondary winding, right? Everybody okay there? So the primary winding points toward the power source. The secondary winding points toward the load. Everybody okay there? Any questions here? One of the rules in your syllabus, by the way, if y'all read the syllabus, is you're not supposed to be texting in class. So if you're doing that, I would appreciate it if you stop. It makes me think I'm very boring. And then we have the core. What's the function of the core? Yeah, to concentrate the magnetic field. Right? Good job. So this is lamination. Since the core is technically a conductor, current called eddy currents will be induced into the core, just like the transfer secondary. The current will be very large because the core itself is going to be large.
So what do? They take that thing and split it into all these laminations. They call it a laminated core. And then they're isolated from each other, and it prevents all those currents from combining. So that's one of the main reasons the transformer will never be 100% efficient. Because it's going to have some core loss, right? You understand? It's just that we limit it. Most of your high efficiency transformers are like 98.5% efficient. So that means we only lose 1.5% of the power inside the core. So that's what I'm passing around, the small transformer. This actually labels the primary and the secondary. This has 3 wires on the secondary. This is what we call a center tap transformer. This is what you have in your house. And then the primary would be over here. Normally these things, they can be wired on different parts of the core. A lot of times they're just twisted right on top of each other. Usually they'll put the primary in the middle first, and then they'll wind the secondary. Yeah. Yeah, that's what they call an E-core. Because if you took it apart like this, so they call this an E-core. Can you see why? And then what they'll do is they'll weld this once they get the windage in there, they'll just weld this bar across the bottom. Now a lot of transformers are going to be in a metal shield, and the metal shield will be connected to ground. These guys put out a lot of electromagnetic interference. I mean, a lot. So we already looked at that. The video explained this really, really well. So what determines? So what you'll see is your high voltage side, the windings will be really, really thin because they have less current. Your low voltage side will have bigger conductors because they got to carry more So if you measure this with an ohm meter, you could tell the low voltage side and the high voltage side. The low voltage side would have less resistance than the high voltage side. Transformer improved efficiency by the laminated core. We already talked about that, right? Creates a change in AC. What determines the power transfer to the transformer would be the load, right? Whatever load you put on the secondary side. So we okay here? Yes, no? So this is basically what's going on. The video showed it really, really well. Now there's a lot to design in the transformer. For one thing, it's got to have opposition. It's got X of L, which we looked at the formula, determined by the number of windings that be there. So it's hard to make transformers, but there's a lot of math to it. But you're not going to design a transformer. You're going to basically. I think somebody made a turns ratio. The voltage in the secondary and the primary don't have to be the same. All right, you understand? So normally we have what we call an isolation transformer. An isolation transformer is just something used to get rid of the ground. Because we're not bringing power through the thing electrically, we're bringing it through the transformer magnetically. So sometimes we need to get rid of the ground, right? So I would use a 1-to-1 transformer. These would be isolation transformers. Besides for those, we have what we call either step up or step down transformers. We do have transformers. I wish I had one of the transformers out of the trainer. I should have brought that over. It's got multi-windings on the secondary, so we can get multiple AC voltages out of them depending on. So some of them are going to step down by different ratios depending on what they do. So we have all types of transformers. On your house, you're using the one at your house is using what we call a center tap transformer. So the primary side, like I said, on the primary side, and then over here on the secondary side, right in the very center, you're going to have a tap. This is what's on your house. So if you ever looked at your house, you got 2 black wires coming down, wrapped around a metal wire, and that's the third conductor. Now, while the third conductor doesn't have a connector is it's actually connected to earth ground. And so that means it's referenced to earth ground. So if you got against it, you wouldn't get shocked. So the third one is used, not only is it used as a support for the other two, it's actually the zero conductor. Now what's nice about this is if I take the voltage all the way across the two outsides, I would get around 240 volts. It depends on how far you are. They guarantee, Alabama Power guarantees are plus or minus 10%. So it could be 10% high or it could be 10% low. Because all their regulation is done at the power plant, right? You understand? And some of your substations have the ability to vary, they electronically vary the number of windings in the secondary to help regulate the voltage on the other side. But it depends on how close you are to a substation. And then if I go between here and here, we get what we call 120 volts, let's say. So what's nice about this, we get two voltages. We get a high voltage, relatively high. High voltage and low voltage is an arbitrary term. In your house, 240 volts is high, what we call high voltage, and low voltage would be 120 volts. Alabama Power wouldn't even think about this. You know, they're up in the thousands of volt ranges. They have what they call a medium voltage. I think medium voltage is anywhere between 25,000 and 50,000 volts. Any below 25,000, they call low voltage. So it all depends on where you're at. So that's an arbitrary term. So this is what you have at your house right here. Now what's on this side over here, it depends on where you're at. There's very few taps. There are some taps up there that the electrician, when they put it up, can move it to get you a small increase or decrease to try to get you as close to these as it possibly can. But those are not guaranteed. So if you're on the low voltage side, your power bill will be probably lower. If you're on the high voltage side, your power bill will probably be a little higher. But it's not enough. It's within the range of the devices that are designed around 240 and 120 so they don't burn up and they still operate within that 10% range. So this is a really good animation, and then all we're doing is changing the turn. We're not changing the turns ratio on the primary. We're changing the turns ratio on the secondary. So we can buy these things that'll either step the voltage up or step the voltage down. We do that over in the robotics lab. We have two robots over there that run off 440, and there is not 440 in that building. So in both of those, we have to have step-up transformers, right, to step the voltage up to run those robots. If we tried to run them on 208, they wouldn't work at all because they would be a quarter of the power, right, and everything wouldn't be right. Basically, all of them are 440. Some of them came with transformers in them. The ABB robot, which is the orange robot on the end, it didn't come with a transformer. And the big FANUC robot it's rated for 440. But its transformer is upstairs somewhere. So this is basically it, guys. Turns ratio, you take the ratio of the primary divided by the secondary, and you come up with a number. If it's a step-up transformer, this will come up and be a fraction. If it's a step-down transformer, this will come up and be a whole number, right? Everybody okay? Very simple formula.
Step up, it'll be a fraction.
Yeah.
Step down, it'll be a whole number.
Yeah. So step up, you're going to get more voltage out. So if you divide by a fraction, right, you understand, you get a bigger number. If you divide by a whole number, you get a smaller number. Because this is the actual formula they look at. The voltage in the secondary will be equal to the voltage in the primary divided by the transfer function. PowerPoints are up on Blackboard, right? Okay. So we take the number of turns in the primary, the number of turns in the secondary, and this is what you would have to know if you was an engineer designing this, because there's a lot to consider. The gauge of wire depends on the power you're trying to get through it, right? So a lot of current, the gauge of the wire would be real big. For small currents, the gauge of the wire would be small for small powers. You have to consider the wire size. How many loops do you have to do to get the amount of impedance in the circuit so it don't act like a short circuit or it don't act like a heavy load? So there's a lot to designing it. Normally this is given to you, so you're not gonna have to calculate this, you can get it. You can get a rough guesstimation by using R, by the way. You can measure the resistance of the primary and the resistance of the secondary, and sometimes that'll work out, but you got to understand that depends on the gauge of the wire, right? You understand? So it's not really, it's also good to know the resistance of the transformer, because this is the one thing, we use what we call laminated wire, because what we're trying to do is inside transformers, we use what they call laminated wire. What they're trying to do is they're trying to get a really, really good coupling between the magnetic fields. So these transformer wires, they basically, all they've got is just a little coat of insulation paint on it. This is called magnetic wire. So this is magnetic wire. So what happens, in fact, some people strip this thing with a cigarette lighter. They'll get their cigarette lighter out and it just burns that insulation off just like that. So instead of stripping it, they'll do it that way, because that painting is real thin. So what happens is these guys are going to be coupled down really, really strong, because you hear those transformers humming, right? You understand what that means is when I put a positive on this side, it creates a negative on that side, and those transformer windings are pulling together. So that's and if you let those windings move a lot, they would chafe off, and then we'd either have we'd short out some of our windings in our primary, or short out some of our windings in the secondary. If you short out a winding, you change your turns ratio, right? So most of the time, if you're not getting as much voltage out that you want, odds are what's happening is windings inside either the primary or the secondary is shorted together. They short together, you change your turns ratio. And there's really nothing you can do with it. You just basically do what? Buy new and throw it away. Yeah. So most of these big high power transformers, once they get them wound, they'll dip those suckers in lacquer and they'll just lacquer them together. Really, so that makes it even harder to change. You'll actually see motors that do the same thing. So motors use this magnetic wiring. So you have to be careful if you see if these things are exposed. You have to be careful. If you hit them with something, it's going to do what? It's going to strip that really thin insulation off. And if you overload the transformer, try to get more power out, and it gets real hot, what could it do? It'll burn that insulation off too. That's usually what happens with transformers. They overload them, burn that lag, and then we have shorts, and it starts burning, or either the wires there will open up. So one of the things you'll do is you'll measure the resistance of the primary and the secondary of this transformer. So this is the way you take the voltage on the primary, divide it by the turns ratio. That should give you the voltage on the secondary. So that means a step-up transformer, then you'll have more turns in the primary than you do in the secondary. You'll have a fraction, right? Understand? For a step up. So for a step-down transformer, the turns ratio would be you need less out, it'll be a fraction, right? For a step-up transformer, it'll be a whole number. Yeah. Good. So a lot of times they don't give you the turns ratio, they give you the voltage in and voltage out. And you can calculate it, right? You understand? So ours is either a 2-to-1 or a 4-to-1. We can wire ours as a 2-to-1 or a 4-to-1. Divide by 4, divide by 2.
Does that relate to the number of fractions of winding? Is that a true number too? There's 4 to 1.
4 to 1. That's exactly right. So if we step down, if we say 4, so if it's step down, then what we would have, and we had a 4, that means if I had 400 turns over here, I'd have 100 turns over there. That's what it is. It's a turn. It's exactly the turn ratio. Good question. Any more? Step-up transformer, the secondary has more turns than the primary. So the transfer function turns ratio would be less than 1. Step-down transformer, the turns ratio would be more than 1. We're okay? Yes? No? No. So these are just basically the same formulas, right? and they transpose them just like we're. Current ratio would be too. You could, and people don't understand that, they got a secondary over here that wants 1 amp. Are you going to put a 1 amp fuse in the primary? No. Because what happens is that if you got 1 amp over here and you got a 5 to 1, right? You understand, then you're only going to have 20 milliamps over here, right? I'm sorry, 2 amps over there. Of course, it's I don't know if there's anything out there on how to fuse a secondary. You actually fuse them for a lot more than what they're rated at. Voltage and current. So y'all understand now so the load has to be designed around a certain voltage. So if the load is designed around a certain voltage, so you'll find out that a lot of your so what's the 3 things that resistors are designed? The resistors are not, so that's not quite true. The resistors are not designed around a voltage. What's the 3 ratings that we need to know about a resistor?
Temperature?
Not temperature. That's not. You can't buy it temperature. If you look up a resistor, temperature is not on the radar. What do you mean by the size? No, it's not rated in gauge. It's not rated in size. It's rated in ohms. No, it's not rated in amps. Huh? It's rated in watts, right? And what's the next one? Starts with a T. Tolerance. So it's the 3 things that resistors are rated in. They're not rated in a voltage.
So it was tolerance,
Ohms. So somebody was saying size. I think when you meant size, that's what you was trying to refer to. But remember, we got a physical size too. So you got to be careful when you say that. So it's ohms, right? Then it's rated in watts, and then then we have a tolerance on how accurate the resistor is. That's for resistors. Most of your loads in your house are going to be rated at a voltage, right? It's going to say, okay, if the load is 240 volts, so if you looked at your air conditioner, it'd say it's going to be able to run on a certain voltage. Resistors are one of the few things that's not rated in a voltage, it's rated in watts. So we'd be dealing with like V square over R, I square R. We built a design, we did a course on designing DC power supplies. We don't do the course anymore because every power supply that you could possibly name, you can do what? You can buy. We used to teach how to fix computers down to the component level, but we don't do that anymore because that's back when a basic computer was well over $2,000 and you could afford to fix them, right? You understand now, if your computer goes out, what do you usually do? Yeah, you buy a new. So when your cell phone goes out, you usually say, well, I wanted a new one anyway. So normally now, power supplies, you just buy the power supplies you need. But we used to teach a class, and one of the things they wanted to do was put a 100 ohm load out there. And several students came up and said, something's wrong with my power supply. It keeps burning up my 100 ohm resistors. Well, guess what they wasn't considering? I think it was 30 volt power supply, V squared over R, so it'd be 30 volts squared over R. How many watts would that put out? A lot more, and they was using quarter watt resistors. So they put that little quarter watt resistor around turn their power supply on, and it would just. So you got to think about that on your resistors, guys. You need to remember, you just can't go out and pick up any resistor, 100 ohm resistor. You have to make sure you understand. You got to buy the right wattage rating, right? You understand, and of course, what tolerance you're looking for. And the lower the tolerance, the more expensive they are. So, a transformer has a primary voltage of 230 volts and a 5 to 1 ratio. What would be my second? So 5 turns for one turn. So that would be 5 divided by 1. So this guy here is going to divide by 5, right? I'm sorry, 1 over. Yeah. So what would be my output voltage? Or the secondary voltage? 230 divided by what? 5. So when they give you the ratios, it's just, this is the primary, 5 turns to 1. We don't know the number of turns. All we know for every 5 turns we have in our primary, we have 1 turn in our secondary. So I mean, this guy's going to divide by 5, right? So what would be my output voltage? What's that? 40 volts. Everybody okay there? Yes. The transformer has 200 turns in the primary, 50 turns in the secondary. So what would my ratio be? It would be 200 over 5, be 4 to 1, right? Put 120 volts on the primary, what we get on the secondary? 30. Everybody okay here? These sound like pretty good test questions, don't they? There are 400 turns of wire in an iron core coil. If this coil is used as the primary transformer, how many turns must be wound on for the secondary to get 5 volts? So we're going from 40 volts down to 5 volts, 400 volts down to 500 volts. Anybody got this one?
This is 400 turns.
Yeah, 400 turns in the primary. So how many turns will we have in the secondary to get 5 volts? Oh, wait. What's missing?
The voltage.
The voltage on the primary. This is not my slide, by the way. So how much voltage y'all want to put on the primary? Let's see, form primary, secondary voltage. Of 1 volt, a primary voltage, a primary of 1 volt. I'm sorry, it is on there. So primary voltage of 1 volt, and we want 5 volts out. I heard somebody say, yeah, we're stepping up, right? So we would have to take this turns and multiply by what? Good. Now, I don't know why I didn't do this. So yeah, I didn't see that either, guys, but yeah, right there. 2,000. A 12 volt transformer has 20 turns in the primary, 5 turns in the secondary. What is the voltage across the primary side? What is the voltage?
3. It's 3.
So we're stepping up, right? We got,
Step it down.
I'm sorry, stepping down. We got 12 volts, right? 20 turns, right? Primary, 5 turns in the secondary. So what is the voltage across the primary side?
2.
3.
1 divided by 5. 4. And 4 divided by 4. 4 divided by 4. 3.
Everybody gets the same thing? Or some of y'all sit back there like this? Don't even have your calculator out. Don't even have your pencil out.
So the
If
one
you wanted to impress an instructor, that wouldn't be the way to do it. Yeah, somebody comes up and says, so-and-so, tell me about so-and-so, he's applied for the job. I said, well, he'll sit around with his arms wrapped around his all the time. So y'all know who I'm talking to, right? So what we get, everybody get this? We can turn this into a test, guys. Y'all want to do that? I want to turn this into. Well, if I say you're going to. So we need more participation in class. Come on, guys.
The answer is 3.
3. Everybody okay on that?
Yes. Good job. Good work.
Everybody understand this? So input and output power of a transformer under ideal conditions, the input power and output power should be the same. So anybody tells you that a transformer changes power, steps power up or steps power down, if it's your boss, you'll just think, so this guy don't even know what he's talking about. If it's your subordinate, you'll say, "Yeah, you don't know." So, of course, we know we have very, very little loss. So from our standpoint, if we're working with one transformer, we're going to assume it's 100% efficient. Why? Because the efficiency is so good. Alabama Power has to really, really be concerned about the efficiency of the transformer. And also their line loss, how much loss they get in those lines trying to send it out. Right? So power in plus the so power out would be, it says plus power, that should be plus the power loss. That's the wrong formula. What should it be? Yeah, should be what? Normally, we wouldn't use that formula. We'd say, oh, I'm sorry. It says power in, so that might be right. Let's look and see what it says. Maybe I need to read it. So power in equals power out plus the power loss. That's okay. That's just not. Usually we say power out would be equal to power in times the efficiency. That's actually the most formula. This formula is right because it's saying power in is equal to power out plus power loss. So how would we calculate the power loss? I took a class when we did this.
Well, no time about the efficiency.
Huh?
Time about what, 95 or 85?
Yeah, but we actually had to measure it. We had to measure it and calculate it. So all we did was measure the current in, voltage out, right? Current in, voltage in, calculated power in, power out, and then we were able to calculate the efficiency of the transformer. So power out over power in. Anytime you calculate gain, guys, it's always out over in. This would be actually what we call an attenuation, which means we get less out and we get in. So this is a formula you're going to run into all the time. Out over in, out over in, out over in. What you get out divided by what you put in. Times 100, and that would give you an efficient in percent, right? Everybody okay? Yes? No? Most transformers are 95 to 98.5% efficient. For this reason, we will assume 100% efficiency during the remainder of this lecture. So it's just easier for us to understand, but you've got to understand, wait a second, you've got to understand that these guys are not going to be 100% efficient. And so that means if they're not 100% efficient, that's why if they were 100% efficient, transformers would not get hot. Because there would be no power loss in the core, right? You understand? If they get hot right off the bat, it tells you right off that these things cannot be 100% efficient. But they're really, really close. So if you understand that, then we can assume, it's just like resistors. Back in DC, if y'all have had DC yet, what did you do when you did your DC lab? What did you do to all your resistors? You measured them. And then you use the measured quantities to calculate your everything in the circuit. Because what you were trying to do is you were trying to prove laws. After DC, you take the color-coded value. You don't try to measure them. You take the color-coded values, and you understand that your calculated values and your measured values might not be exactly the same anymore. But they're going to be close enough, right? You understand? So that's just like here. So here we'll say, okay, 100 watts here, 100 watts there. We know we might be putting 100.5 watts over here to get 100 watts over there due to the efficiency of the transformer. We know that. But for all practical purposes, we're going to assume these guys are 100% efficient, even though they're not. We're going to need a break. Y'all need to talk to Mr. Foster about if you want a 30, we usually take 30 minutes worth of breaks. Well, I'm sorry, this is 4. We usually take 40 minutes worth of breaks. Normally what we can do for this class, and you can tell them it's okay with me, is if he gives you two 5-minute breaks and then gives you a 30-minute break for lunch. That would be your call. That's your call. Right? You understand that? So y'all need to decide on that as a class. But only 5, so the breaks that you'll be getting, instead of these 10-minute breaks, you're only gonna get what? 2 5-minute breaks, and then a 30-minute lunch. So, and then you can decide if you want to take that 30 minutes lunch during the class, or if you want to take it at the end of class. That would be you. I think the class goes to 1:15. We're doing 10 minutes today. Or we could not take a break. Yeah, we can do that. Yeah, but y'all gotta realize that you need to vote on this as a group and not set it by 2 people. Huh? So let's vote. Who wants to go straight through and take it off at the end of class? Okay, majority rules. So that means if you gotta go, you need to do what? You need to get up and hustle, right? It is, but you still have to find what you missed, the 5 minutes that you missed within a. So that means what time will we get out? 12:45, okay. Well, the class goes to 12:15. I mean 1:15, so it'd be 12:45. So we're not taking a break. Y'all all voted to do the 30-minute thing, right? So these are the types of transformers. These are power transformers, control transformers. This is basically the only one we're going to discuss this one. We have distribution transformers, we have isolation transformers, and we have auto transformers. If you're going to take a break, y'all need to not get out as quiet as you possibly can, right? So a control transformer is used to reduce the voltage from the main power source over to what we need. Everybody okay? So this is our transformer. It's a dual voltage transformer. It looks kind of weird, right? So we have 2 primary coils. We have one called H1 and H2, and then we have one called H3 and H4. So on transformers, industrial transformers, usually they don't specify step up or step down. They use H for the high side, so that's where you'd put your high voltage, and then they use X's for the low side. They don't use L's because L's has already been taken up for inductors. So X is for the low side, right? You understand, and H is for the high side. That would be for your high voltage and low voltage. So we could use this to step up as long as we didn't exceed the voltage rating. So we could bring it in here and go from, well, we can wire this as 4 to 1 or 2 to 1. So we can step it up by 4 or step it up by 2, or we can come over on this side and step down by 4 or step down by 2. Okay.
So when we wiring these, will we stagger them or will we offset them? Like H1 and H3 or H1, H2, or would it actually matter?
No, you have to hook them up right, because what would happen is if you hook them up when this one's going out, if you hook this one up backwards and it goes in, it would cancel each other out. So you're going to have to wire them in a certain sequence depending on whether you want to divide by 4 or you want to divide by 2. Now we'll explain why do they have the symbols crossed in a minute. Okay. So notice they have it crossed. So H1 and H2 would be this coil, and H2, H3, and H4 would be this coil. And then we have X1 and X2. This is what we have. The only thing they've done for us is on ours, they've actually got a fuse right here. So they're not calling it X1. They're going to call it XF because it's on the other side of the fuse. Are we okay so far? So a lot of people don't understand why they cross it. And I'll show y'all, it's a really, really good example. In fact, I'm going to go ahead and get one of these off. They'll have to just come up and work. You're going to be jumping this out with jumpers. But when you buy the transformer, basically you got these little metal tabs that you can set it up for divide by 2 or divide by 4. So what we want to do is, it's just like sources. If I hook sources in parallel, what do we get? If I hook sources in series, let's think about batteries. If I hook batteries in series, what does that do? Yeah, it increases the voltage. So the voltage is added, right? We add the voltage if we hook them up together. If we hook DC sources in parallel, what do we do? Let's see if I can get this thing. Okay, there we go. So if I've got DC voltage sources, and then I hook them in series, and you run into this all the time just in your remote controls, right? You understand? Then what happens when we hook them in series? Then, it does. If you take the negative and hook it into the positive, now if you take the negative to negative, they cancel each other out. No, I just can't draw the little line over here for some reason. Where am I at? And you'll run into this. Let's see if I can get this. I can't get my pen to work on it.
Series aiding and series opposing.
Yeah, we can hook batteries series aiding, or we can hook them up series opposing. I got to get this. Yeah, so you can hook DC sources. Now AC, you got to be really careful because of the phase. To hook up generators in parallel, they literally have to sync them. It's a really neat feature. So you need to, and they'll sit there and run speed one up a little bit, slow one down a little bit until they get in phase. You just can't drop generators in parallel, AC generators in parallel. DC, we could do that, no problem. We can come up here and we can take DC sources and we could hook them up in series. Of course, if we hook them up in series, if this is 1.5 volts and this is 1.5 volts, if I measure the voltage across, then we would get 3 volts. But we wouldn't increase the current. So if these batteries were rated at 100 milliamps, then we would get 100 milliamps because current is the same in a series circuit, right? Understand? So I hook DC voltages in series DC sources in series to increase the voltage, not the current, the voltage, right? You understand? If I take those same batteries and I come up here and I hook them in parallel, I'm having problems with my drawer. Now, what's this going to do? It's going to increase the current. So if we hook DC sources, and you'll see your remotes do that. More of the time, they'll hook them in series to get the voltage up, because if the voltage up, the less current required to produce the less current required to produce the power in there, right? Sometimes, though, we actually need current. We can't have extremely low current devices, so your batteries will be hooked in parallel. So a lot of times, you'll see 4 of them. You'll have 2 in series over here, 2 in series over here. Then if you looked at the wiring, that actually the two would be in parallel. So you get 3 volts, but if your batteries are rated at 100 milliamps, then you'll be able to get 200 milliamps at 3 volts. So we hook them in series to increase the voltage. We hook them up in parallel to increase the current. So what we're going to do is that if I if I want a divide by 2, then we need less current, we need less turn ratio in the primary side. But if the voltage goes down, the current is going to have to go up in the primary. So what we want to do is we want to split those currents between the two coils. Because this coil might be rated at 1 amp, this coil might be rated at 1 amp. If we hook them in parallel, then we can put 2 amps into the thing, right? You understand? So that means if I'm going to do a divide by 2, what I'm going to do, if I can get my pen to work, what I'm going to do is I'm going to take my primary and I'm going to hook my primary in parallel, because that way the current is shared, right? You understand? Yes or no? So that means what we got to do is we would have to come up here. Okay. So what we'd have to do is we'd have to come over here and take the primary, and we would have to come up here and we would have to connect them in parallel. And then our secondary would just be like that. So that means if this guy's rated at 1 amp, this guy's rated at 1 amps. Now what I've done is I've changed my turns ratio, right? You understand? So right now, so we'd have to hook them series. So what it means over here, I would have to take H1, and then I would have to connect this to H3, because if I connected to H4, then my second one would be upside down. And over here, this would be H2, and this would be to H4. And then over here, this might be X1 and X2. Everybody okay there? That makes sense. Now, if I do a divide by 4, then I'm going to double my turns ratio in my primary, which means now it requires less current. Over here, I'm putting 2 amps in, so here I'm putting 2 amps in over here, right? You understand? But if I go to twice the voltage, then it's going to be what? It's going to be half that. So what we need to do is take these things and we need to connect them in series. So this would be for low voltage. This right here would be for high voltage. So now what I've done is I've increased my turns ratio. I've doubled my turns ratio on my primary. So my transformer is going to divide by 2 more, right? You understand? So this is going to be H1 if it writes. So this would be H1. This would be H2. This would be H3. And this right here would be H4. Everybody understand that? Okay. So what we're trying to do is when you buy these things, these multi-voltage transformers, they're going to come with these little metal tabs. And those metal tabs are, what we want to do is we want to be able to jump these things without having any crossing lines. So what that means is if I come over here and connect this thing like this, notice they're in one parallel. But my jumper is going to be between H1 and H3, and my jumper is going to be between H2 and H4. These are connected in parallel. So what this would be, I got 400 turns over here, I got 100 turn over there. This would give me a divide by 4. Everybody understand that? I'm sorry. We got 200 turns here in parallel with 200 turns here. So that's not 400 turns, that's 200 turns, right? You understand, because they're in what? They're in parallel. So this would be a divide by 2. Well, I hook them up in parallel because if my current in my primary goes, if my voltage in my primary goes down, the current's got to go up to produce that power. But notice I don't cross any wires, right? You understand? So if I've got a little metal tab, all I have to do is put the metal tab between 1 and 2, 3 and 2 and 4. Now, if I'm going to wire it the other way for high voltage, then so that would be like this, right? So H1 to H2. No, this is wrong. And this was, I made the correction on the bottom, but I didn't make the correction on top. So this is a PowerPoint I got off the internet. So you got to double check PowerPoints off the internet. So what would this be? So let me come up here. I'm going to insert a text box. So what would this one have to be? So this is gonna have to be what? H3, right? Because this is the second coil, sorry. I thought I corrected this. Nope, it's wrong field, Rich. And then this one down here would be what? It's 4. So we got H1 to H3 and H2 to H4, right? Everybody okay? You understand that? It's still parallel. Yeah, you can see they're in parallel. Parallel means they're connect. The two ends are connected together, right? Yeah. So that means the turns ratio is still this one right here. So it's a 200 to 1 turns ratio because they're connected in parallel. I think, let's see if the guy put this one right. This would be a divide by 4. So he's got this one right. He or she's got this one right. So these are connected in series. So we come through here, go down through here, and these are connected in series. So this would be a 400 to 1. But what I want you to notice, why they cross those like that, and this is the way it's wired, so I don't have any crossing wires, right? You understand what I'm saying? Yes or no? So how would we connect the coils in parallel? Calculate the secondary voltage and primary voltage is 48. And the number of turns in each primary is 50 turns. So what is it? And the secondary turns is 25 turns. So how would we connect it in parallel?
In parallel, you go from
I might be able to do this with my mouse, guys. In fact, I can probably do it that way. So if we was going to connect them in parallel, all we do is put a jumper between here and here and here. By the way, we always bring it in on, your voltage always comes in on H1 and H4. Even though you could bring it in H2, it's just this is industry standard, right? Y'all understand that? It's not drawing. Okay. I don't know why I won't draw down there. I guess it's too close to the bottom. Okay. That's what I should have been doing. I should have been selecting my pen with my mouse. So this would be wired for what? Low voltage or high voltage? Be low voltage. They're connected in parallel, right? Okay. So what are they saying? They says connect the primary coils in parallel and calculate the secondary voltage of the primary. We have what? 48 volts. Okay. And what else does it tell us?
50 turns.
We have 50 turns in each primary, so we're not concerned with each one of them. For both of them, all we're doing is concerned with one of them, right? And 25 over here. So is this guy going to step up or step down? Step down, good. So what would my output voltage be?
What would your secondary voltage be?
Yeah, what my secondary voltage be? 24, right? It's a step down. Good. Right? 50 to 25. I'll have a step down of 2, right? 2, and then we'd say 48 divided by 2 would be 24. Good. Yes, no? Everybody okay? Need me to get up here and pose in front of them? I get up there and point. We had the first group of bros that come through, and they was going to take pictures over there on our amateur line. And then the technical photographer was over there, and they said, Looks like you're doing something, so guess what they started doing? Turning knobs. And we got over there, and the line wouldn't even run, we had to figure out. Looks like you're doing something. So they turned knobs. That was group one, that was group one, by the way. Connect the primary in series. Oops. Oops. So if it's going to connect them in series, what would we do? Guys, as soon as I can do this. All we have to do is just put a jumper between 2 and 3. Now they're in series, right? You understand? We have 50 turns here. Now we're going to have to consider the 50 turns on the other one. And what do we have over here? So here we have 48 volts. Primary has 48 volts. So what would we get on the output? 12. This is going to be 100. So it's going to divide by 4, right?
Four in series and two.
Huh?
So you divide by 4 when it's in series and two.
That's exactly right. Yeah. Because you double the number of turns. So when they're parallel, you're lowering the voltage, which means the current has to go up in the primary to create that power. So the windings are only designed around a certain current, right? You understand? So in parallel, each one of them would get, like I said, if each one of them needed 2 amps, then that would be split. If the primary needed 2 amps, it would split between the two, right? Here, if we put them in series, then we require less current to do what? To provide that power, right? So now if they're rated at 1 amp, this would be 1 amp and this would be 1 amp. So in parallel, the current splits between the two, and the turns ratio is the ratio of one of them. Here you'd add the ratios, you'd add them together, right? Makes sense? And normally you don't know this. They'll say, like on ours, it says, okay, if you looked at the nameplate, it'd say, if you put 480 in, you're going to get, if you put 480 in, if you divide by 4, you're going to get 120 out. If you put 240 in, you'll get 120 out. But that's on the transformer. But you got to understand, if I wanted to divide by 4, I don't have to put 480 in this thing. I could put 120 volts in it, right? You understand, and get a divide by 4. And what would I get out of it? Yeah, so that would give me a 30 volts. So these transformers, they'll give you 1 voltage. Normally the transformers don't give you the turns ratio, but they give you the voltages that it's set up for, where you can calculate the turns ratio and you could get anything you wanted to. So I could bring my input into the low side, take my output on the outside, and I would get, and if I had it hooked for high voltage, I would get, it would be a multiply by 4, right? You understand? Or I could get a multiply by 2, depending on where I go. So most of your industrial transformers don't say primary and secondary. They say what? High side and low side. And you know the high side because those terminals are going to be labeled with H's, and your low side is going to be labeled with X's. And we have multi-tab, we have multi-winding transformers. So here, if I hook them in series and then I hook these in parallel, I would be able to get more current out. So I hook these in the series. This would be a 4, right? This would be 200, and this would be, if I wire these in parallel, this would be 50, right? You understand that? Yes or no? But what I would do is I would be able to get twice as much current out of my secondary. So you get all types of variations of transformers. You have transformers that have multi-windings on the primary. You get transformers that have multi-windings on the secondary. You have center tap transformers, which is what's out there on your house. So your house has a center tap transformer. So what does that mean? You get 2 voltages. You get 240 nominal voltage, and you get 120 just by doing a center tap transformer. The only problem is on 240, it doesn't use ground, right? It doesn't use neutral. So in Alabama Power, they don't call it ground. They don't call it common. They call it neutral. And neutral is a grounded conductor. Your neutral is connected to ground. So what's the difference between the neutral and what's the difference between the ground? Well, the neutral conductor is supposed to carry current. The ground conductor is not supposed to carry any current. If you get current flow in your ground, it means you got a what? You got a problem. And that's what your ground fault circuit, your GFCIs do. They're ground fault circuit interrupters. If they get current, if the current in the so the current in your both sides should match, right? If they don't match, then what does it do? It trips it out. So if you get across an outlet, guys, your GFCI is not going to protect you. Your GFCI, if you get across those neutral and those hots, you're going to be considered a light bulb, right? So it's not going to get you from getting interrupted. Let's see if they got anything else here. I guess that's all. We can get multi-tap primaries. I'll try to show y'all in fact, I can do that real quick. So anybody used the trainer yet? You hadn't used not in here, not this trainer, the electronic trainer for the electronic classes. DC, intro, you ever use those trainers? How many voltages do you have available on that thing? You have some fixed voltages. You have a plus 12 and a plus 5. Then you have some variable voltage where you can adjust them from anywhere from 0 to around 15 volts, right? I'm trying to figure out where I've got the schematic for the trainer at. I know where to be. I know sideways, this is hard to see, but this is the actual power. You know, this is good. This is the actual power supply right here. So this is the transformer there. It's got 1, 2, 3 winders on it. 2 of them are center tap. So you have 6.3, you have a 12.6 volts transformer here. Since it's center tap, you can get 6.3 here, 6.3 there. You'll use that in, I don't know if you don't use it in AC. I think you use it, I know you'll definitely use it if you take solid state. Then we take this transformer. This goes to a unit that converts AC to DC. Then this is the capacitor. It filters it. And then this comes out to an electronic regulator. It's a 7805. So this is your 5-volt power supply. This is your 12-volt power supply. So we have plus and minus 12. And then these two right here are your variable regulators. So this would be the actual rheostat. So pot wired is a rheostat, and the ones you can adjust your voltage on. But that's the transformer on that. So the transformer here has 1 primary, and then it has 1, 2, 3 secondaries, and 2 of them are center tap. So you can run into transformers in all different types of arrangements. We have transformers that have multi-taps on that. Besides the center tap, it has multiple taps, and you get multiple voltages on there. Here, so this is the actual schematic on the trainer. This is called a rectifier bridge, by the way. So this is actually what's converting AC into weird DC. And then here's a capacitor. We're using it as a filter. And then these are your regulators. These are what actually sets your output voltage. And then these are the LEDs that light up when you don't burn one up. So if you get down there and you turn on the trainer, and one of these LEDs don't light up, you need to say something's wrong because that's on the outputs of your regulators. And you need to. And we had one of our instructors that would get out a permanent marker and write bad on them. And what do we teach here? We can fix, these things are easy to fix. So we can fix it. We got all the parts. We can fix any one of them. So if you got one that's bad, you need to let your instructor know and we'll get it over to my shop and we'll fix them. Yeah, these are easy to fix. So that's transformers, guys. Y'all got any questions? So there should be a topic quiz on Blackboard. If he did, Mr. Foster did the syllabus quiz, the syllabus. It said that topic quiz is due within 7 days after we finish the lecture, right? So there should be a topic quiz. I think it's assignment 3, I think. You go up there, it's going to be on basic electricity theory. Anything y'all want to go back over? Huh? Because I'm through. I'm
So
not
it'll
going
be
to
doing
go. Huh?
Wednesday, it'll be doing Monday.
No, it'll be due next Wednesday, right?
Oh,
7 days. Y'all get 7 days. Yeah, no, 7 days. 7 days. You get a week to do these topic quizzes. The lectures, well, like I said, this lecture I'll put up there. The other lectures I didn't record. So if you go to the Blackboard site, you'll see it says previous terms. That should be the lectures the last time that I taught the class. And they should be in Becky's, I think they're called Electricity 1, 2, and 3. So if you missed any of your lectures, y'all can go up there and look at that, right? You understand that? And then I'll put the transformer lecture up there too. Everybody okay? Syllabus, you were supposed to do the syllabus agreement before this class, right? I guess I should go look at that. The assignment 1 is due by Friday midnight, right? You understand that? And then assignment 2 is due by next Friday. You got those 2 assignments. There's several assignments. All the assignments are in the assignment section of Blackboard. I need to look, make sure y'all look at that. But what I'm saying is I'll go ahead and put this on the calendar. But that assignment 3 will be due by next Wednesday. I think it's, let me make sure. I might have another class. Y'all know I teach a few classes, right?
Mr. Foster by chance leaving the silver.
He should have. Yes. The briefs. There you go, Lee. Oh, yeah, I was fixing to say Mr. Feltman didn't get in this class, did he? Didn't it, Feltman? Yeah, they put him in another schedule. Because he actually came in after y'all, didn't he? There's no topic quiz for transformers. It's later on. It's as you go through the course. It's basic electricity. Here's motor controls. Only got its one right now. That's it. If you need one,
These are all LT.
194. Huh?
Yes.
They're up there. They're on Blackboard, Lee.
The syllabus is on.
Yeah, the brief is on there too. But if you want one, I can run you off, but you'll have to hang around.
It's on Blackboard, I think.
Yeah, it's in first week in course information, then syllabus and brief, and there should be a copy of this up there. Hold on just a second, guys. So assignment 1, assignment 2. So assignment 3 is the quiz on basic electricity. This is assignment 3. Assignment 3 is the quiz on the material covered, the basic electricity lecture and the textbook. Click on the assignment 3, and the due date is when? Before next Wednesday. I'll put it on the calendar. Everybody okay? So all you have to do is click on there. There's nothing on transformers in this because you'll have it in your labs. There's actually quizzes on transformers in your labs. Okay? Everybody okay? Stick a fork in me, I'm done.